require it. Okay. So, let me see how I'm moving. Okay, so it is the same. Yes, it is the same. If you
one is derived from lambda.
yes, you can have the same, and it will be the same result. I think that.
Is that assumption or requirement?
One second, because there is something missing here. I think that one can prove it. And maybe I had this as I think that I had this even as an exercise. Now, of course, it is my last lecture, but if you have questions after that, until I'm here, you can always come and ask, of course. Okay. Now, we have some additional things which we shall use. We have this thing. I should change this, or maybe it can be pumped, or no. Not this kind, okay, doesn't matter. So we have also the notion of opposite co-multiplication. Which is delta prime, and it is equal to pi. So you take first delta and then you take pi, and pi is the permutation of two elements. So pi on x tensor y is y tensor x. Now it may happen if delta prime is equal to delta, then delta is called co-commutative. Co-commutative. Now we said that it's not necessary that gamma squared is equal to identity, or that, which means actually that gamma is equal to gamma minus 1. In fact, it's not even clear where gamma, yes, because, no, sorry, this is not correct question. And of course not clear, but if it exists, no, this is not right. But sometimes it can exist, and then gamma prime is equal to gamma to minus 1. So this is called opposite antipode. Like here, opposite antipode. So it may exist, may not exist. It exists. It is there. And now we come to the point where we can say what is quantum group. More precisely, of course, I should say that sometimes quantum group is not a well-defined option. And for instance, the best book on quantum groups by Charry and Presley, it does not have a definition of quantum group, because I will give definition and then I'll say that it may be not, that one can maybe not give example. So let's give some definition. So quantum group, that they are the quantum group, or the same way it will be called quasi-triangular, Hopf algebra. Is a Hopf algebra irreducible element R, which belongs to the tensor product of U times U, which is called universal R matrix. Universal matrix, such that it has the following property. If Y is an element of U, you have the following equality: R times delta of Y is equal to the opposite coproduct Y times R. So R is an element of U times U, and delta prime of U is an element of U times U, so you can multiply those, and you can also take delta of U and then multiply with R after the delta. So if this is true, then of course we have a quantum group. Of course, it has also to obey the following relations. We have to obey the following relations. The relations are as follows. Now we have delta times identity times R. Here one has to be very careful because there are now I will explain what 1, 2, 3 means. So this equality is acting on 3 times on the triple tensor product. And for instance, the notation R13 means that that R belongs to the first factor U, and so to the first factor and the third factor. You understand? R is an element of U times U, and here we have 3 times U. So I can put the R to belong here and here. And then I call it R13. And if I take R23, it means that it belongs to U on second position times U in third position. And here I didn't put anything, and this means that here it will not matter. It will matter that R can be here I'll write this as R dot 3. And dot 3 means that the second factor belongs to 3 and the first factor can be in 1 or 2. It doesn't matter. And there is an additional relation in the way in which 1 and 3 are interchanged. Which 1 and 3 are interchanged. Now here we have R12, which is analogously to R13 and R23, means that R is supposed to be in the first and the second. We have the R13 which we have used, and the R here which is here R1 dot. Means that it can be in second and third position. It is similar to the first one, just somehow rotated.